Good morning, sir.
So we are in the analysis of group 2 cations. General discussion is completed for separating group 2 cations. In this group 2 analysis, important point is separation of all these cations into 2A and 2B by dissolving in YAS, polyyellow ammonium sulfide. Then only sulfides of arsenic, antimony and tin dissolves in YAS and form soluble complexes. Now let us move to some individual experiments. Test for mercuric ion. These experiments explained by taking mercuric nitrate as an example. The first one is with ammonia solution. It forms a white precipitate, HGO, HgNH2NO3. This is called basic mercury amido nitrate. Basic mercury amido nitrate. This basic word because of this HGO, mercury amido nitrate. Where mercury, both mercuries are same oxidation state, +2 and +2. And second one with NaOH solution. Adding NaOH in stoichiometric amounts. That means exact amounts without adding any excess. We are getting yellow precipitate of HGO. This HGO insoluble in excess reagent NaOH. So what type of oxides? What type of metal oxides soluble in NaOH means amphoteric character metal oxides is also NaOH. Remaining metal oxides are insoluble in strong bases like NaOH. Next one is cobalt thiocyanate, very important in the case of mercury. COSCN taken twice. Cobalt thiocyanate. This color also very important, deep blue. In practical chemistry, this is one important color, blue color. Whenever you got blue color, please highlight that blue color complex or compound or precipitate, whatever it, anything related to blue. So deep blue crystalline precipitate is obtained. In this complex, COHGSCN taken 4 times. COHGSCN taken 4 times. Cobalt is available, mercury also available, both metals are there. But regarding mercury, one small confusion, because mercury has 2 oxidation states, +1 and +2. I mentioned here +2, but please justify, here I mentioned +2 no, for mercury. Why I am putting only +2, why not +1? Anybody, Nana? For mercury, I put here +2 in the complex. +1 also possible, no? If you put +1, why it is incorrect? +1 mercury is not given in the complex. Only +2 I mentioned here. Anybody? Mercurous, mercury, 2 mercuries are there. In the complex, I placed only +2, but not +1. This Hg +1, mercurous ion, mercuric ion. Mercuric ion representation Hg2 plus, but mercurous ion is a dimeric ion. Dimeric means it is represented as Hg2 2 plus. But here in the complex, Hg2 is not there, no? That's why it is +2 mercury. Suppose mercurous chloride, Hg2Cl2, mercuric chloride, HgCl2. Not like that. So since Hg2 is not there, it is +2 mercury only. So CO, Hg, SCN taken 4 times. Its IUPAC name, I am writing here IUPAC name, cobalt, oxidation state 2, tetra, thiocyanate, S, amidite ligand, mercurate, anionic complex, and 2. What about this complex, para or diana, this complex? Total complex, para or dia. So, but total I am marked here total complex, because if you take only coordination sphere, it is diamagnetic nana. What is coordination sphere? Hg, SCN4, 2 minus. That means here Hg2 plus is there. It has D10 configuration, zinc family nana. Therefore, this is dia. But outside metal is there, no, cobalt plus 2. That is paramagnetic nana, CO plus 2, 3D7. So it is para. So if you consider only coordination sphere, it is diamagnetic. Total complex is paramagnetic only. So para is correct. By considering CO plus 2. C is correct for coordination sphere. Hg, SCN taken 4 times, 2 plus. That's in the question. If they ask only coordination sphere, diamagnetic. Overall complex means we have to write paramagnetic. Very important complex nana. CO, Hg, SCN taken 4 times. Deep blue color precipitate is obtained when cobalt thiocyanate is added to mercuric nitrate salt. Next one, potassium iodide. Another important experiment, potassium iodide. We are getting red precipitate of HgI2, mercuric iodide. This HgI2, by adding excess potassium iodide, that precipitate dissolves and form colorless HgI4 2 minus. If it is potassium iodide, that's why it is nothing but K2HgI4. K2HgI4. This K2HgI4 very useful reagent for detecting ammonium salts or ammonia, mainly alkaline solution. Alkaline K2HgI4, including alkaline, is called Nessler's reagent. Only K2HgI4 is not Nessler's reagent. Alkaline K2HgI4 is called as Nessler's reagent. This Nessler's reagent used to identify ammonia or ammonium ion. This K2HgI4, potassium tetraiodado, mercurate 2. Potassium tetraiodado, mercurate 2. Alkaline solution is called as Nessler's reagent, used to identify ammonia and ammonium ions. Two important reactions are these two, third one and fourth one, with potassium thiocyanate and with potassium iodide. Red precipitate of HgI2, it dissolves by adding excess potassium iodide into formation of soluble colorless K2HgI4. That alkaline solution of K2HgI4 is known as Nessler's reagent, used to identify ammonia or ammonium ion. Next one with SnCl2, stannous chloride. Stannous chloride, one point I am writing here, carbon family. In carbon family, if you take lead, stable oxidation state is +2 due to inert pair effect. IPE I am writing. In inert pair effect. If you take tin nana, so its stable oxidation state is +4, not +2. Only for lead bottom elements influenced by inert pair effect. Thallium in third group, last element. Lead in fourth group, bismuth in fifth group. Stable oxidation states are lower oxidation states. So down the group in P block elements, lower oxidation states are stable due to inert pair effect. That's why if you take PbO2, if you take SnCl2, this is +4, this is +2. So this Pb +4, try to convert it into Pb +2. This Sn +2, try to convert it into Sn +4. So PbO2 readily undergoes reduction, SnCl2 readily undergoes oxidation. That's why this SnCl2 act as reducing agent, PbO2 one of the important oxidizing agents. That's why SnCl2 in this reaction act as reducing agent. So first it gives white precipitate of Hg2Cl2, mercurous chloride, and by adding excess SnCl2 further reduced to black mercury. So here Hg+2, Sn+2, Hg2 2+, again Sn+2 gives Hg. So +2, +1 and 0. So this one act as a reducing agent. This Hg2Cl2, electrochemistry also very useful compound it is. It is called as calomel, secondary reference electrode. These 3, 4, 5, there is specific experiments for mercuric. One is cobalt thiocyanate, blue precipitate. Another one is potassium iodide, red precipitate, with SnCl2, white precipitate first, and slowly converted into black mercury Hg by adding excess SnCl2, because SnCl2, I think in your organic reactions also, in number of cases we are using SnCl2 as reducing agent, because for tin +4 is more stable. So Sn+2 readily converted into +4 undergoes oxidation and act as reducing agent. This is about mercuric salt, mercuric experiments. Next we have test for bismuth ion. This is explained by using bismuth nitrate, BiNO3 taken thrice. Actually, Nana, for explaining this practical chemistry, generally we are taking nitrate salts. Why not other salts means most of the nitrates are water soluble. That is the advantage, Nana. Most of the nitrates are water soluble. That's why analyzing becomes very easy. అందుకనే మీకు మినరల్స్ చూస్తే if you observe ores or minerals, nitrates are very, very less we have. Mostly we have sulfides, sulfates, carbonates. Like that we have but not nitrates. Nitrates very, very less number because of their water soluble character. In the first experiment with the sodium hydroxide, it gives white precipitate, BiOH taken thrice. Because of basic, it is soluble in acids but insoluble in NaOH. Only amphoteric character hydroxides or amphoteric character oxides soluble in excess NaOH. So soluble in acids, insoluble in excess reagent, that is NaOH. Boiled, then it becomes yellowish white, BiOOH, precipitate is obtained, and with potassium iodide, black precipitate is obtained. that is BaI3. That BaI3 with excess potassium iodide, it gives orange colored BaI4 minus. On hydrolysis, it gives BaOI, orange colored precipitate, but this BaOI contains BaO plus, I minus. These are called as BaO plus are called as oxocations. We have oxoanions, nana, like sulfate, phosphate, carbonate. These are all oxoanions. But we have some oxocations also. It's a good example. This is called as bismutyl iodide. Bismutyl iodide. So BaI3, BaI4 minus, BaO and hydrolysis. Warming. Orange color, here also orange. And precipitate BaI3 is a black colored compound. Next one, next experiment with sodium tetrahydroxostanate. That means Sn plus 2 in alkaline medium. Tetrahydroxostanate. Tetrahydroxostanate 2. SnOH4. Now we need plus 2 oxidation state. Plus 2 oxidation state means charge is minus 2. Once again, tin is in plus 2 state, Nana. If tin is in plus 2 state, act as reducing agent. So it reduces and gives black precipitate of bismuth. Previously we got BaI3. Now Bi, both are black in color. So alkaline medium, what happened? Bismuth plus 3 first reacts with a strong base like NaOH and gives white precipitate of bismuth. That white precipitate of bismuth hydroxide becomes black by adding a reducing agent, that is SnOH4 2 minus. Now this one SnOH is 6 2 minus. Tin is in plus 4 oxidation state. This is called as hexahydroxo stanate anionic complex. The bracket 4. This is a redox change. Plus 3 to 0 and plus 2 to plus 4. With sodium tetrahydroxostanate 2 with Sn plus 2 in alkaline medium, it gives a black precipitate. Next one is with pyrogallol. In this practical chemistry, we have a small topic, Nana. Importance of organic reagents in inorganic analysis. Very important topic, Nana, for competitive examinations. Importance of organic reagents in inorganic analysis. After completion of this, in one class, I am giving all those reagents at one place. Okay, pyrogallol, like that we have. Pyrogallol 1, 2, 3 trihydroxybenzene. It gives yellow precipitate BiC6H3O3. Pyrogallol trihydroxybenzene C6H3OH taken thrice. It gives yellow precipitate. C6H3O3. Pyrogallate, we call it as bismuth. Pyrogallate, yellow color precipitate is obtained. So 4 experiments for the identification of bismuth. Next experiments we have lead ions. First one is with dilute HCl. It gives white precipitate of PbCl2. It is soluble in hot water. One important solubility nana PbCl2, PbBr2, PbI2. These three soluble in hot water. Not only in hot water, it is also soluble in concentrated HCl or concentrated potassium chloride, and gives a soluble fluoride complex. Tetrachlorido plumbate 2 ion. Anionic complex plumbate 2 ion. Next one with dilute H2SO4. It gives a white precipitate of PbSO4. That PbSO4 lead sulfate soluble in hot concentrated sulfuric acid or ammonium acetate or ammonium tartrate. So PbSO4 soluble in hot concentrated sulfuric acid, ammonium acetate or in ammonium tartrate. Next with NaOH, sodium hydroxide, white precipitate is obtained. That is PbOH taken twice. Dissolves in excess NaOH because lead compounds are amphoteric character. Here I am writing important amphoteric oxides. If oxide is amphoteric, nana, its hydroxide also amphoteric. Al2O3, one previously also given, I am recollecting, ZNO, BeO, U2O5, Cr2O3, oxides of tin, no lead. These are all important amphoteric oxides. One more point, if oxide is amphoteric, its hydroxide also amphoteric. If oxide is amphoteric, its hydroxide also amphoteric. So amphoteric nature oxides or hydroxides are soluble in strong bases like NaOH. Amphoteric oxides or hydroxides soluble in strong bases. Otherwise, metal oxides insoluble in NaOH or KOH. Only amphoteric nature oxides, hydroxides soluble in excess NaOH and form PbOH4 2 minus. Tetrahydroxo plumbate 2 ion. To this tetrahydroxo plumbate 2 ion, tetrahydroxo plumbate 2 ion. If you add hydrogen peroxide, good oxidizing agent, it can act also reducing agent, but preferably oxidizing agent. Then Here MRC PbOH42 minus, lead is in +2 state, converted into +4, so oxidizing agent. Here S2O8 minus, this is also oxidizing agent. My anion of Marshall acid, H2S2O8. H2S2O8. This H2S2O8 is peroxo disulfuric acid. That's why this is called as paradisulfate. Very good oxidizing agent. So those oxidizing agents oxidizes PbOH, PbOH42 minus 2, PbO2. Powerful oxidizing agents, Nana. Next one is potassium chromate. So lead salts reacts with potassium chromate and yellow precipitate is obtained. That is PbCrO4. Nitric acid dissolves the precipitate and this yellow colored lead chromate becomes orange colored dichromate because of acidic medium. Now we have a conversion, chromate CrO42 minus and the dichromates are interconvertible. This is H plus, this is OH minus. That's why by adding nitric acid, this chromate converted into orange color dichromate. And one more point is, most of the chromates are yellow in color. Except Hg2CrO4, Ag2CrO4. But these two are red in color. This lead chromate PbCrO4 in painting, very useful compound. This is called as chrome yellow. Lead chromate is called as chrome yellow. This is about lead potassium chromate reaction for lead. Next one with potassium iodide. An important experiment, Nana. It gives yellow precipitate of PbI2. PbI2 moderately soluble in boiling water. By adding boiling water, it dissolves and gives colorless solution. On cooling, I think you heard about this one, Spangel's experiment. Golden yellow plates are separated out. Spangel's test. Spangles means shining crystals. So by dissolving in water, we are getting clear solution. PbI2 yellow. By adding boiling water, we are getting colorless solution. That solution on cooling, golden yellow color shining crystals comes out. That's this experiment is called as Spangel's test. If you take PbCl2 or PbBr2, white color, then we are getting white crystals comes out on cooling. Because yellow color, on cooling, yellow color crystals comes out. Golden shining crystals of yellow, called as golden yellow Spangel's. Spangel's test we call it as with potassium iodide. Yellow precipitate PbI2 moderately soluble in boiling water. This is about important experiments for lead. Next, bismuth. Before that, mercury salt. There were 3 important cations in second group analysis. Next one is group 3, third group analysis. In third group analysis, 3 hydroxides are there. FeOH taken thrice, CrOH taken thrice, aluminum hydroxide. This FeOH taken thrice is red brown, chromium hydroxide green, aluminum hydroxide white color precipitate. To this group 3, first we have to add sodium peroxide or NaOH plus H2O2. Out of ferric hydroxide, chromium hydroxide, aluminum hydroxide. Aluminum hydroxide is amphoteric. Chromium hydroxide also amphoteric because their oxides are amphoteric. These two also amphoteric. That's why this chromium hydroxide and aluminum hydroxide, these two only dissolves in NaOH. The two we are adding hydrogen peroxide. So hydrogen peroxide also act as oxidizing agent. So CrOH taken thrice, AlOH taken thrice, both dissolves in NaOH, but not ferric hydroxide. And even though we are adding hydrogen peroxide, already iron is in +3 oxidation state. So further oxidation is not possible. That's why by adding Na2O2 or NaOH plus H2O2, ferric hydroxide is separated out. And chromium hydroxide, aluminum hydroxide dissolves. And that too H2O2 oxidizing agent. Aluminum already is in +T state. That's why further oxidation is not possible. But for chromium, oxidation is possible. For chromium, IST is +6. That's why 2 reactions, chromium hydroxide dissolves in NaOH and simultaneously undergoes oxidation also. Whereas aluminum hydroxide only dissolves in NaOH, but further oxidation is not possible. Ferric hydroxide insoluble in NaOH and further oxidation also not possible. That's why ferric hydroxide separated out and chromium hydroxide, aluminum hydroxide dissolves, plus that chromium is in +3 undergoes further oxidation. And that's why in filtrate we are getting 2 compounds, CrO4 2- and aluminum hydroxide. Here chromium is in +6 oxidation state, aluminum is in +3. That's why this chromium hydroxide dissolves or I'm writing the point here, H2O2 oxidizes, H2O2 oxidizes chromium hydroxide to chromate in basic medium. But in the case of aluminum hydroxide, further oxidation is not possible. That's why it remains in +3 state, but soluble complex is obtained. Tetrahydroxo aluminate 3 complex. Tetrahydroxo aluminate 3 ion is obtained. A very important point. In group 3 analysis, they selected Na2O2 or NaOH plus H2O2. Aluminum hydroxide dissolves in NaOH, but it won't undergo further oxidation. Chromium hydroxide dissolves in NaOH and undergoes oxidation, gives chromate. Ferric hydroxide insoluble in NaOH and further oxidation also not possible. Next, test for aluminum ion. Test for aluminum ions with ammonia solution. white gelatinous precipitate of aluminum hydroxide. This aluminum hydroxide slightly soluble in or insoluble in excess of reagent. Ammonium hydroxide nana, ammonia solution and ammonium hydroxide, weak base nana. Ade aluminum hydroxide, if you add NaOH, then it dissolves and form aluminate. So it is insoluble in excess ammonia. Even though aluminum hydroxide is amphoteric, but ammonium hydroxide is weak base. Generally, amphoteric compounds reacts with strong acids, strong bases. See, next experiment is NaOH. White precipitate is obtained aluminum hydroxide, and this aluminum hydroxide now dissolves in excess reagent NaOH. This is strong base and form aluminate tetrahydroxo. Aluminate 3 ion is obtained. So aluminum hydroxide, amphoteric, H4OH, NaOH, dissolves. Here no reaction. This is strong base. This is weak base. Slightly soluble, almost insoluble. Difference between ammonia solution means ammonium hydroxide and NaOH. In both cases, we are getting white precipitate, but these two white precipitates insoluble in ammonia solution and soluble in NaOH because of its strong basic character. Next test for chromium. Chromium plus 3 with sodium hydroxide. Green precipitate is obtained. CrOH taken thrice. Because chromium hydroxide is amphoteric, dissolves in excess reagent NaOH, like aluminum hydroxide. Strong base. And we are getting CrOH4 minus complex, green solution. To this by adding hydrogen peroxide in basic medium. Just now I told it acts as oxidizing agent, and plus 3 compound is oxidized to plus 6 with we are getting yellow solution. That too strong base. What is the base now? Here NaOH and we are getting yellow solution of Na2CrO4 sodium chromate. So chromium hydroxide dissolves and further oxidation takes place. By dissolving, it gives a green solution of CrOH4 minus, and by adding hydrogen peroxide and basic medium, and it gives yellow solution of sodium chromate. Next, chromium plus 3. Extra information I am giving here, because our compound also CrOH taken thrice. NaOH H2O2 or bromine water in alkaline solution. NaOH plus H2O2, bromine water, chlorine water act as oxidizing agent and becomes chromate, because bromine water gives BRO minus hypobromite ion, hypobromite, hypochlorites. These are all good oxidizing agents. NaOCl, NaOBr, sodium hypochlorite, sodium hypobromite, good oxidizing agents. Hypochlorite, hypobromides, oxidizes chromium plus 3 to CrO4 2 minus chromate, and to this by adding dilute H2SO4, ether or amyl alcohol in the presence of hydrogen peroxide, it gives blue coloration. CrO5 peroxy compound. It has butterfly structure on a CrO5, and by adding barium chloride, it gives yellow precipitate of barium chromate. Right hand side I am writing CrO5. This is the structure of CrO5. This oxygen -1, -1, -1, -1, -2. ఏమవుతుంది chromium plus very important CrO2 taken twice ఇలా రాస్తాం నాన్న దీన్ని. This is peroxy linkages. So it has 4 peroxy oxygens. That means 4 oxygens with -1 oxidation state. Butterfly structure we call it as. Two peroxy bonds. 4 peroxy oxygens. Careful. Peroxy bonds and O bond. Individual oxygens are called peroxy oxygens. So 2 peroxy bonds. 4 peroxy oxygens. Or 4 oxygens with -1 oxidation state. Then the CrO5 stable in organic solvent like ether or ML alcohol. అదే ఆర్గానిక్ బదులు మీరు aqueous solution వాడితే ఇక్కడ చూడండి ఇచ్చాను. In aqueous solution, the blue color fades rapidly. CrO5 decomposes to Cr plus 3 and O2. Generally in aqueous solution, Cr plus 3 is in green color. So blue CrO5 converted into green in aqueous solution or excess acidic medium. As long as you maintain organic solvent, it is stable CrO5. That point also, please highlight this ether or amyl alcohols. Dilute sulfuric acid, hydrogen peroxide. Gives blue coloration, once again blue color. Previously we got one blue color COHCSC and taken 4 times. Now one more blue color we got, that is CrO5. Next, one of the most important cation in the cationic analysis, test for ferric. My very point important, Nana, for ferric ion. Carefully practice thoroughly all the experiments, colors, precipitates, and solubilities with ammonia solution. In ammonia solution, ammonium hydroxide, Nana. A reddish brown precipitate is obtained of ferric hydroxide. It is insoluble in excess of reagent. It is not amphoteric, Nana. That too, one more point I am giving. Generally, transition elements form complexes because ammonia is one of the important ligand. But this is one of the transition metal compound, hydroxide, unable to form complex with ammonia. Then solubility చాలా తక్కువ, KSP value very low. Ferric hydroxide, among hydroxides of transition metals. This is one hydroxide of transition metal, insoluble in excess reagent. Most of the transition metal hydroxides are soluble in excess ammonia due to formation of soluble complex. In highlight just called insoluble in excess of the reagent. But this ferric hydroxide on heating gives ferric oxide, red brown precipitate. Ferric hydroxide on heating converted into red brown. Next with NaOH, sodium hydroxide, same red brown precipitate, ferric hydroxide, insoluble in excess reagent, that is NaOH, because this is not amphoteric. Amphoteric oxides, amphoteric hydroxides generally reacts with strong bases, but this is not amphoteric. Very important, none of this one separately I am writing. Ferric hydroxide, insoluble in ammonia solution and insoluble in sodium hydroxide. Next with H2S in acidic solution. H2S, one of the important reducing agent, Nana, because in that H2S, sulfur is in least oxidation state of -2. Therefore, H2S act as reducing agent. But our iron is in +3, Nana, that is important. Because Fe +3 higher oxidation state, so it can act as oxidizing agent. That's why redox reaction takes place. Fe +3 ions are reduced to Fe +2 and sulfur is formed as a milky white precipitate. దీన్ని మనం colloidal sulfur అంటాం. Colloidal sulfur, elemental sulfur, almost white, almost pale yellow color. Pale yellow means almost white. So Fe +3 plus H2S, here reducing agent, oxidizing agent. The sulfur is called colloidal sulfur, pale yellow, almost white precipitate of sulfur is obtained when ferric salt reacts with H2S. H2S acts as reducing agent and ferric salt acts as oxidizing agent. Redox change takes place and we are getting a green colored solution. Green coloration comes out. Suppose our ferric salt is, example, I'm taking FeCl3. Then we are getting FeCl2, ferrous chloride, green coloration. This ferric chloride is yellow color compound. Redox change takes place. So with ammonia solution, red brown precipitate. With NaOH, red brown precipitate. And both are insoluble in excess ammonia solution and excess NaOH solution. And with H2S, it undergoes redox change and ferric becomes ferrous. H2S converted into colloidal sulfur, pale yellow or milky white precipitate. ఇవి మనకి నాన్న ferric salt with ammonium thiocyanate gives blood red coloration. That blood red colored compound is FeSCN taken thrice. ఈ షీట్ చాలా ఇంపార్టెంట్ నాన్న. బ్లడ్ రెడ్ కలరేషన్ ferric thiocyanate. Ferric thiocyanate. Next, ferric salt with potassium ferrocyanide. Potassium ferrocyanide. It gives once again intense blue precipitate is obtained. My very famous name, no, called as Prussian blue. So Fe4, FeCN taken 6, whole taken thrice. It is a combination of two ions, Nana. One is ferric ion, our salt, and FeCN6, 4 minus. A combination of these two gives Fe4, FeCN taken 6, whole taken thrice. And if you take one molecule of Prussian blue, we are getting 7 ions. And in that, outside iron is +3, inside iron is in +2. Next, with K3 FeCN taken 6 times, potassium ferricyanide. With ferricyanide, it gives brown coloration of FeCN taken 6 times. Iron is in +3. So that is also important. In Prussian blue, both irons are in different oxidation state. And in brown coloration, obtained when ferricyanide added to ferric salt, in that complex, both irons are in the same oxidation state. So first complex, and one more point is, you must see here, this is +3 outside, this is +3 outside, and here also outside +3. So in both complexes, outside iron oxidation states are same. But inside, if you observe +3 here and here +2, so we can reduce +3 iron to +2 iron by adding suitable reducing agent. See, hydrogen peroxide, SnCl2, act as reducing agent, and by adding suitable reducing agent, we can reduce the coordination sphere iron +3 to Fe+2 coordination sphere iron. Two more points I am writing here. So FeCN taken 6 times. Okay, both irons are in +3 oxidation state. Its IUPAC name is iron 3. Hexacyanido, my anionic complex, no? Ferrate 3, IUPAC name. Next, Fe4, FeCN taken 6, whole taken thrice. Outside iron +3, inside iron +2. Therefore, this is called as iron 3. Hexacyanido, ferrate 2, iron 3, hexacyanido, ferrate 2. Prussian blue and brown coloration. చాలా important on this particular 3 experiments are ferric with ammonium thiocyanate, blood red coloration, a ferric thiocyanate with potassium ferrocyanide, Prussian blue, and with potassium ferricyanide, brown coloration takes place. This is about third group analysis. Okay, 2 more groups are there, 4th group, 5th group, and 0 group. Tomorrow, let us complete that cationic part. Then anionic analysis, reactions of anions. Okay, tomorrow I'll continue the remaining part.
సార్ ఈవినింగ్ క్లాస్ ఉన్నా సార్ మీది?
చూస్తానమ్మా, టైం చూసి పెట్టుకున్నాం.
ఓకే సార్, ఓకే సార్,
రైట్ రైట్.
థ్యాంక్ యూ సార్.
రైట్.
Thank you, sir.